All right, so one of the things I showed you yesterday, and this is a visual representation, and I won't turn the sound on here, is that if the source is moving, then what happens is the waves in front get compressed together, right? To really exaggerate this, that's actually not really that great, is it? Let's take a look at the other one. Let me take a look at the other one that I had. Maybe I'm on the wrong day. Oh yeah, I'm on the wrong day. There we go. Yeah, this one was maybe a little bit more visual. And I showed you that the waves in front are crowded together, right? So that means if you were standing, say, where that number 10 is, or where that 15 is, or where that 20 is, that when those waves pass you, they pass you more frequently, which means the frequency is greater, right? But what I didn't explain is why, if you're moving, do you hear a higher frequency? Because if this is stationary, if this source is stationary, the waves are the same distance apart everywhere, aren't they? But if I'm passing from this point to this point, I'm moving in this direction, then that means that I'm going to be crossing the ripples faster than the ripples would be passing me if I were standing still. So if I'm moving towards the source, it isn't that the wave fronts are crowded together, it's just that I'm passing them quicker. And somebody had mentioned yesterday near the end of the day, they caught me at the end of the day and said, well, how come you hear a higher frequency in this situation, but the wavelength is the same on both sides? Yeah, the wavelength is the same, but I'm passing the waves more frequently, so the frequency I hear is greater. Anyway, what we have with yesterday's lesson ultimately comes down to you understanding when the frequency is greater, when the frequency that you observe is less. And we have this formula for the apparent frequency, what you hear being the speed of the sound wave over the speed of the sound wave plus or minus the speed of the source times the frequency of the source. And we said that if the observer is moving, just wrap your head around how the source would have to move if the observer were stationary, and go with that. If they're both moving, wrap your head around how the source would have to move if the observer is stationary. And whether it's plus or minus depends on whether the frequency goes up. If the frequency goes up, then you're going to have on the bottom minus. Because to get a larger frequency mathematically from that formula, that fraction has to get bigger, which means the denominator has to get smaller. If the frequency that you observe goes down, then that means you have to add the speed of the source. Take a look at your work, please. Does anybody have any questions here? Jay? 5 and 6. Okay. So you have a whistle that's traveling south, and you are traveling north. Okay, so but you were going towards the whistle, and that's interesting because you just did that, what I just saw you do, which was you pointed your fingers this way, and I went, wait a minute, that's not what I thought was happening. I thought this was happening. And I was immediately going to say, we have to be told somewhere whether they are approaching each other or going away from each other. And they are approaching each other. So, think about this for a second. If the whistle were stationary and I were getting closer to the whistle, would the frequency I hear be more or less? Okay, good. If I were stationary but the whistle were coming towards me, would the frequency I hear be more or less? More. So these two effects are going to add together, which is why when we take a look at number 5, and we start, as I say, wrapping our head around, let me mute that. As I say, wrapping our head around which way the whistle would be moving if we were stationary, we're going to add those two speeds together. So I have on the one hand the whistle, and clearly the whistle isn't a sentient being traveling south. It's in a car or on a bike or something. But this is moving at 27 meters per second south. You were moving towards it at 15 meters per second. The relative speed of the observer, and it's not too early to review this. We studied relative motion problems in Unit 1. If Peppermint Patty is 100 meters in front of me, traveling east at 4 meters per second, and I'm running behind her towards her at 5 meters per second, how long does it take for me to catch up? We're not going to solve that problem, but I'm just reminding you. The relative speed of the observer is 42? Is 42 meters per second toward the source, or the relative speed of the source is 42 towards the observer. The bottom line is that change in velocity is going to be 42. That Vs is going to be 42. And I realize right now that when I wrote this, let me write down the formula. I wrote this to talk about V of the observer, but do you see that I could say that, Jay? Okay. So Vs is 42. We've already established that these two things are getting closer to each other, which means the ripples are going to be both compressed closer together because the whistle is moving, and I'm going to be passing them even quicker because I'm moving over the ripples towards the source, which means that we're going to have here a subtraction. Exactly. So what is the speed? 341 over 341 minus 42 times the frequency that the whistle has. You know, I want to say that the frequency that the whistle has objectively, like there is a frequency that's being produced. Something is wobbling in the whistle at that number of times per second. And that, hopefully it will work. I'm getting, that cannot be right. Thank you. So I am getting 2281 hertz. If the decimal's off a bit, is that a concern? Don't let it be. I think I entered the numbers in right. Wow, that's off quite a bit, isn't it? Oh, I wrote the frequency down wrong. It's 2500 hertz. I apologize. Just all right, I'm getting my groove here. There we go. So I'm getting 2.85. The answer says 2.83. It should be 2.85. Okay. I'll have to fix that for next time. You said 6 as well, though, right?
Well, they're basically the same question. I just messed up on the direction.
Okay. So I just want to take a look at 6. If I do take a look at 6, this time we're going away, And that means that the relative speed will still be 42, but we will have to put plus because when you're moving away from the source, the frequency is less. And in order to get less, you're going to have to add that number on the bottom to get a bigger denominator. Any other questions? Go ahead. Number 7? So you're traveling towards a stationary whistle. The whistle is stationary. The apparent frequency of the whistle is 3,130 hertz, but the frequency of the whistle, objectively speaking, is only 2,900 hertz. So just to begin with here, if the frequency of the sound produced is 2,900 hertz, but you're hearing a higher frequency, then you have to be traveling towards the source. Yes? Okay. Now, we have a bit of a problem here, and the problem is that the source, let me write this down first. The problem is that in your formula, and we've talked about this a lot of times so far, but in your formula, that Vs on the bottom is not the speed of u, it's the speed of the source. But if I'm saying, I want to pick a number here because we don't actually have a speed. If I'm telling you that I travel 5 meters per second towards a source, then that could be accomplished by me standing stationary and having the source travel 5 meters per second towards me. So we can always just talk about the speed that the observer moves relative to the source as being the same as the speed that the source moves relative to the observer. So even though it says we're trying to find the speed of the observer, let's find the speed of the source. And I know this is getting repetitive, but then we will know how quickly the source would have to be moving towards me for me to hear that, which would be the same as the speed I would have to be moving towards a stationary source. I hope that makes sense, everyone. So what do we know? We know that this is 3,130. That's what 3.13 times 10 to the 3 is. We know that the speed of the sound is 343. We know that the frequency of the whistle, or whatever it is a whistle, is 2,900, objectively speaking. And then we have this plus or minus what is in fact going to be our answer, right? But since we're hearing a frequency that's higher than the frequency that the whistle has when it's not moving, this must be minus. And we can go ahead and put Vs here, or you could put VO. It doesn't matter. Now, how do we go about, what's the mathematics of this? Well, there are things we could do to rearrange this equation which are less work than what I'm going to show you. But I've tried to teach you in math that when you're solving an equation, one of the things that makes things simpler is no fractions. So I'm going to multiply both sides by the denominator here. And I'm going to get 343 minus our answer times 3130 equals 343 times 2,900. Are you with me on that? Okay. Unfortunately, what your Math 9 and maybe even your Math 10 or Math 20 teachers tell you is we should get in the habit of multiplying things out before we solve. And I think that's not a good move here. Since we want to get Vs and Vs is in the brackets here, why don't we just divide both sides by 3130 right now to get rid of that number? If you multiply it in, then you're going to have to figure out what 3130 times 343 is, and you're going to have that minus 3130 Vs. It's going to be a nightmare. Well, not a nightmare, but you know what I mean. It's going to be more complicated. So I can now take 343 minus Vs and write that's equal to 343 times 2,900 over 3130. And this thing that's on the right-hand side, everybody, is just a number. You can figure out what it is. 343 times 2900 divided by 3130. I've messed up some numbers already today. Is it 3130? Okay. So now what I have is 343 minus x equals 317.8, 5, whatever. So to find x, I can swing the x to this side where it becomes positive, and the answer is going to be 343 minus that 317 point whatever. I'm getting about 25 meters per second. I don't know why all of my answers are off slightly. That's really weird. Yeah, I don't think I've done anything wrong there. Correct answer should be 25.2. Not blaming anybody else because I'm responsible for this, but I think maybe I must have just pilfered these questions from some resource and not checked them. Or when I made the key, I was just having a really bad day. Anyway, is that okay? Okay. Any other questions? All right. So we're going to move on today, and we're not learning a lot of new content today, but we will be doing a little lab activity together. I had the best intentions of you doing the lab on your own, but I needed to go buy some materials from Dollarama for us to do the lab, and I had some transportation problems yesterday at the end of the day, so I couldn't get there. So we're going to be doing this together. Okay? Well, you're going to be doing it together. I'm going to be calling up people to collect data and help me out, because it is a lab that you can't just do on your own. You need more than two hands. But before we get to the lab, which is going to be determining the speed of sound, we are going to be looking at what are called standing waves. And I have already talked to you about standing waves. We'll get to a definition in a second. But, and you can draw this certainly. Don't worry about writing down the definition. A standing wave is a wave that's on a string, usually. It doesn't have to be. Where the ends of the wave can't go anywhere. So for example, if I create a wave on a guitar string, it's confined at both ends. And as a result of that, what actually happens is the wave travels in one direction, it hits the fixed point, and it reflects back. So when you have a guitar string and it's wired between these 2 points, and you pluck it, and you get that tone, and you get this shape happening. If you take a look at the shape of the string, it's all blurry, but you understand what I mean, right? This is just a two-dimensional thing, though. It's not like me swinging a skipping rope, like we were doing in the atrium. What's actually happening is you're creating a wave that's traveling from the first point to the end point and reflecting, and it's reflecting in such a way so that the waves traveling to the left and the waves traveling to the right overlap in this beautiful pattern. But the frequency of vibration to make this happen is governed by a number of things. It's governed by the mass of the guitar string. It's governed by the density of the guitar string. It's governed by how long the guitar string is. It's governed by how tight you wire the guitar string. And we're not going to get into the formulas that do that. But this frequency is only possible with a certain guitar string. And with that same guitar string, you can get it to oscillate so that you get a wave traveling to here that reflects back and matches up with the wave traveling to the left. So the reflected wave and the original wave are oscillating in kind of unison. And I'm not very happy with that diagram at all, so I want to redraw that. That's a little better. And what happens is you get this point here, this point, and this point, which are all stationary. And, you know, in retrospect, I'm not sure how much we need to write definitions in words. I'm not sure how much we need to write definitions in words, because I can tell you right now that these fixed points are nodes. And I remember what a node is by seeing that the word node has the word no in it. And a node is a place where there's no energy. Now, you cannot just take any string and get it to vibrate in this way up top where you have 2 nodes, or in this way where you have 3 nodes, or maybe where you have 4 nodes. Because there are natural frequencies. So for example, if I take this string, and I start turning this end, I'm not getting any nodes, am I? It just looks like a big slinky. But if I can get the right tension, there we go. The right frequency and the right tension, do you agree that's a standing wave? It has one, It has 1, 2, 3, 4 nodes, yes? The 2 nodes at the end, and then 2 more in the middle. I mean, I also have this thing, which isn't as noisy, but it's a little more delicate. Right now, that tension in this bottom string, can you guys see it from the far side of the room? Come over here so you can see it. Please. And for some reason, I think it's maybe easier to see if I hit it with a bit of light. Or maybe not, we'll find out. No, it's easier to see with the lights on. I'm going to turn it back on, and I want you to take a look at the bottom string. It's actually kind of a plasticky string. Come up really close, like you can't really see much from there. Like, there's a node right here, right?
Yeah.
You can come over here too, or stand right here. There's a node there. Oh, there's a nice one up top with 4 nodes. And the natural frequencies that you can use to create these are determined by the tension in the string. So I've lost that top one, haven't I? But I've got something going on here. I have a feeling my batteries are dying a bit on this motor, but there's a nice one on the bottom. But if you take a look at this, oh, there's a really good one on the bottom. Look at that. 1, 2, 3, 4, 5, 6 nodes I count. But I can't just have this vibrating at any frequency and expect to get something. Whoop. Oh. All right. So at a certain frequency, I get 3 nodes. If I lessen the frequency, I don't get 3 nodes. I get 4. If I go to a higher frequency, I can keep 3. Well, it's kind of coming in and out here. How many nodes on the top one? Just 2. And it depends on, the tension as well. If I do this, I don't know if you can see that. I'm getting
4 on the bottom.
2 there, 3, 4 on the bottom now.
It was 3.
Was 4? Now that one changes. There's a lot of variables here. Okay, so have a seat again. I'm going to try this with the drill and see if I can get some more interesting patterns.
Thank you for not spinning your arms quick.
That's hard work. This is hard work too. So I don't know that I can just get 2 nodes. I think no, I don't think I can. Nodes? Is it a standing wave? Okay. Is that a standing wave? Is that? I don't think these are standing waves right now. I think it's just like a spiral. That's definitely a standing wave, yes? There's a good one. Be careful because that thing's going to break and somebody's going to get hurt. All right, do you get an idea of what a standing wave is? It's a wave that's confined between 2 ends, and it has what are called nodes. So if you want, you can write under nodes that it is a region where there is no energy or a very, very tiny amount of energy. Do you agree that in all of these examples that I've been showing you, the node hasn't been perfectly stationary? Well, actually, this thing, some of these nodes here on the green strings, they're really fixed, aren't they? So we just say there's no energy. That would mean, by the way, that points like this or this, these are antinodes. This becomes a very important idea for Physics 30 when we talk about interference of light, that an antinode is a region where you have a buildup of energy. And we're going to study, I don't know if we'll get to it this week, it will probably be when we return, something called interference of waves, and that's exactly what is happening here. The wave traveling left to right on the string is interfering with the wave that reflects back, and where the waves have antinodes, each of the 2 waves have energies that are adding together and interfering to produce more energy. But what's happening where they have nodes, it's hard to imagine because you don't see it, but at a node, you have the crest of one wave meeting the trough of another wave and they cancel out. You get no energy there. You don't see the crest and the trough because they cancel. Any questions with standing waves or what a node or antinode is? Pretty straightforward. We're going to look now at resonance in tubes. And we're going to be talking about sound waves. I have a real cool video, by the way, I have to find it, of standing water waves. I had a cappuccino maker, not a cappuccino maker, an espresso maker at one point. And when the pump was working, it would vibrate the water in the tank. And it vibrated the water in the tank in such a way that the waves were reflecting back and forth, and then they would stand. And it was literally that shape on the surface, and it was just sitting there, kind of drifting a bit, a little bit this way, a little bit that way. And I'll find that video to show you. But we're going to be talking about standing waves for sound. And Resonance in tubes occurs when a standing sound wave reflects through the bottom of a closed end of a tube. And I have one here. I have a tube, and it's open on the top and it's closed on the bottom because there's water here. And the nice thing about this is I can adjust the length of the tube. I can make the tube longer. If you look at the water, this air column is longer. I can make the tube shorter. Whoops, I have to get that off of here first. There we go. I can make the tube of air shorter. And the lab that you were going to do, I have a whole bunch of glass tubes. I just needed to buy some like narrow garbage bins that we would fill with water so you could put the tube in the water and raise or lower the tube. But as I said, I couldn't get that yesterday. So resonance occurs when we start a sound wave and it travels down the tube and it reflects off of the water. Now, this is just like the standing wave situation we saw here. When the wave travels down the string and reflects off of the string, if the frequency is right, then you get a nice standing wave. Okay? But for us to get a standing sound wave, we have to have a certain length of tube. Just like for you to get a standing string wave, you have to have a certain length of string and tension, and there's all kinds of variables. So what's happening is when I strike this, it's pretty boring, I know. Sound is traveling towards the surface of the water, which is the end of that tube, and it's reflecting back up. But I want you to notice something. Can you tell me about what height that water is at?
28.3.
28.3. Can you tell me, does that say 384 hertz?
Yes.
Okay. 28.3. Nope. Can you help me, Alex? Would you like to hold this just for a second? Thank you. Something happened there. What happened was when the water got to a certain length, the sound got louder. And the only explanation there is that the sound is getting louder at an antinode in the standing wave of sound. And that's what we call resonance. Now, that happens for different lengths depending on the frequency. So this was 384 hertz, and what is the height of the water right now?
Like 15 exactly.
15 exactly. Okay. Now, it happened at a different point there, didn't it? And there's a connection here between the wavelength that's created in there and the frequency and the speed of the sound. And that's what the lab is going to be that we're going to do in a second. But let me move this up so that it doesn't fill up this too much. You understand what's happening here is the water is leveling out. As I bring this cup up, there's more water above, so it's going to equalize. And when I bring it down low, there's more water below, so it's going to equalize. It's just a way for us to change the length of the air. So this is what we call constructive interference. When that length of that tube got to a certain length and you heard the sound increase momentarily to a higher volume, what's happening is you're getting an antinode in the standing wave there, and that's called constructive interference. You will also find there will be points where it gets very quiet. So it isn't just one volume of sound and then it gets louder. It usually starts off quiet, grows, gets really loud, then diminishes, and you will get a point, if you're patient enough and you have good enough hearing, where you don't hear very much. Talk more about that in a minute. But here's the question, which is going to lead us to the lab activity that we're going to be doing together here today. Why is the shortest length of a tube that produces a resonant, constructive sound always 1/4 of the wavelength? So if I start up here with a length of the tube, and by the way, remember the length of the tube is the amount of air in the tube. The sound reflects off of the water. And I go with I'm going to go with this one again because it's nice and loud. What are we at there? About?
11.5.
11.5 centimeters. I better go to a different one. Give me 1 second. We'll try this one. Does that say 288 hertz?
Yeah.
Okay. So what happened about here? Let's keep going. Pretty quiet all of a sudden. Very quiet. Still going though. You'll discover that where it gets the quietest will be twice the length as where it was the loudest. And the question is, why is this distance? So I'm going to draw a tube here. All right. So we have this tube of air. And I know the tube doesn't end there, but there's water there, right? So this is the tube that goes down, and this is H2O here. So the tube effectively ends there. Okay. Why, if we hear constructive sounds, also known as resonance in the case of sound, it's constructive interference. Why is this distance 1/4 of the wavelength? That's what the question asks. And I don't know that anybody's going to figure this out. But at the same time, I don't want to assume that you can't. First of all, to give you a hint, you're not going to be able to wrap your head around this if you think of sound as being a longitudinal wave, which it is. It's compressions. You have to think of it being a standing wave that looks like one of these. That looks like one of these. Now, would you agree? I hope, if you can't see that, I'm going to draw that. Right now on the bottom string, there's a node here, and a node here, roughly. I'm kind of losing it, but which means this is what you're looking at. Would you agree that is a full wavelength? That's one wavelength. So my question to you is, why are we getting constructive interference at 1/4 of the wavelength? And now I think you can almost see it, right, Jay?
That's where energy is the most.
That's where the energy is the greatest. That's where we get antinodes. And what actually happens here, and we don't need to get into the precise details of why, when that sound wave reflects off of the surface, that is going to produce a node. And if we're going to get maximum sound here, that means that this is an antinode. Now, there may be other places in the tube where you get a maximum resonance or a maximum sound. For example, and I want to go to one that's going to produce a very, very short number for the resonance. We're going to do 512 hertz. Oh, that is almost overflowing. We're going to do 512 hertz. What distance are we passing right now, Alex?
You're just passing 47 and a half.
Okay, good. Do this just a second here. We're just past 47 and a half. Okay, so.
Now it's gone up.
Yeah, now where are we at now?
About 35 and a half.
Okay.
36.
All right. So we'll go from the top down. It will go faster. I'm going to just wait for this to go up. And Alex, you're going to let me know when the length of the air column has passed 10 centimeters. And it does slow down as it gets higher up because there's more weight on this water in the column right now. Where are we at about?
12-ish.
Okay. All right.
It stopped at 11 and a half.
Okay. So I'm going to need your help. When I say so, what you're going to do, and you don't just let gravity take it over, you're going to move this down to about here.
All right.
Okay? Go ahead. Thank you. I think we missed it. I'm going to go back up. We don't have to do them both at once. I want you to see if you can get a maximum hearing of this. What are we at?
22.
Okay. Taking a long time. Oh, that's because this is wrapped up here. There we go. Would you agree that's a pretty short tube at the top? So this will be the shortest length that will produce it. Okay, there was one there, wasn't there? That was at about 16. So let's just think about this for a second. If that was at about 16, and a full wavelength, and again, I'm drawing a transverse wave here, but a full wavelength is that distance, and this happened at about 16 centimeters. Can you figure out where it should happen again? 48? Okay. I don't know if we'll get to 48, but I'm going to try. I think it went below 50 before.
I think so.
Okay. So, can you show me where 48 is?
Right here.
Okay. All right. Keep your finger there. It was there. Maybe not exactly 48, but it was there. Actually, there it is, isn't it? It might have been, I might have heard it get louder because I maybe moved the tuning fork a little bit or something, and we had a better resonance or a better reflection there. So the idea in this lab that we're going to do is with a number of tuning forks, we're going to try to measure the wavelength so we can find the speed of sound in the air. So for example, if I go with, well, let's estimate this. And then I'll give you a handout for this lab. Can you do me a favor, Alex, and tell us what that frequency is on that tuning fork?
280.
288? Okay. I would like everybody to find the wavelength of the sound that 288 hertz will produce if the speed of sound in this room is about 233 meters per second. Okay, so we have a speed of 233 meters per second. We have a frequency of 188 hertz. The formula you can use to determine the wavelength would be speed equals frequency times wavelength. It's not a difficult calculation. But while you're finding that wavelength that tuning fork will produce, I'm going to hand out the lab that we're going to record our data on and that you are going to be doing your calculations with. I'm guessing it's going to be less than 2 meters, but more than 1 meter. What did I say? 333 meters per second? Divided by 188 hertz.
288.
288. My mistake. 333 meters per second divided by 288. Probably very close to 1, like 1.2-ish. Okay? So think about this for a second. In your chart here for tuning fork frequency, you are going to put 288. Now, someplace in here, we're going to get the shortest length of air that we will get acoustical resonance happening. But rather than me just starting at the top, we already know what the wavelength of this is, right? 1.2-ish meters. The length of the air column that should produce that maximum sound should be a quarter of that. Which is what, Alex?
Roughly 0.29.
0.29. So about 29 centimeters. Well, that gives us a region to focus on, right? I know that it's going to be around 29 centimeters. And 29 centimeters on here, I'm just putting some marks so I can see it. 29 centimeters is about here. That red mark is just for me. So that's where we are going to be listening very carefully, and Alex is going to be reading the level of the water when we hear it. Okay. Thank you.
It peaked at around 29.
Peaked at around 29, okay. Now, keep in mind we did that calculation so we knew where to look, but we can't just say, oh, it's 29 because we calculated it to be 29. It peaked at 29 because it peaked at 29. So that's what you're going to record for the length of the air column is 29 centimeters. We're going to do one calculation together. We're working backwards now. You don't know the speed of sound in the room. I said use 333. I just made that up, and we're going to be doing that in a second too, looking at the temperature. But if this is the length of the air column, the third column in your table says wavelength, right? So if it was 29 centimeters, and by the way, Alex would be the first to agree, you can't say 29.3 or 29.6. It happens quick, right? I suppose you could really slow down the rate at which the water is moving, but we're not going to worry about that. What is then the wavelength? Well, that length of the air column is 1/4 of the wavelength. So you would have to multiply that by 4. And you get 1.18 meters, I think. 1.16. So 1.16 meters. Now, how would we find the experimental value of the speed of light? Experimental, not looking at the thermometer or the thermostat. Well, we know the frequency and we know the wavelength. Speed equals frequency times wavelength. So if we multiply that 1.16 by the 288, what we will have done is measured the speed that sound travels at in this room. Wow, that sound travels at in this air column, which, you know, if the water was very cold, then the air temperature in the tube would be very low. But it's pretty much room temperature. So what do we get? 288 multiplied by 1.16 gives you 334 meters per second. And I don't think we really have the right to put any more significance to those digits at the end. 0.08, like, come on, look at this apparatus. This is just roughly eyeballing it, right? I mean, it does have numbers on it. Now, let's do, that was 288. 288, if I go to a lower frequency of no, let's go to a higher frequency of, I think that says 384.
Yes.
Okay. So where will it peak at about 384? Well, let's not try this time with, I can't move it down anymore. Let's not try it by calculating it first. I'm just going to get this going, and we're going to move this down. And we don't know where it's going to peak, right? We really don't. Oh, come on. Forgot to loosen that. Okay, we're ready to go.
About 20 and a half.
20 and a half, 20.5. So this was $384. From here on in, we're not going to be doing all the calculations together. You said 20.5 centimeters. So don't worry about any calculations here. Let's move on. Let's go to 256. We did 288, we did 384. No, let's do 320. So this is going to be 320. You can record 320 in your table next.
$25.5.
25.5. Now it's interesting to note here, well, I think it's interesting anyway. You said 25.5? These are all in centimeters, and this I said was 320. It's interesting to note, or it's worthy to note, that 320 hertz is between 288 and 384, and 25.5 centimeters is between 20.5 and 29. I mean, that makes sense. Let's move on. Let's do a different one. Let's do, I hope we get enough room in the air column for this one at the beginning. 426.7. I have no idea why this is 426.7. It's got the letter, I think a G stamped next to it. No, A stamped next to it. So I don't know. Must be a musical note. Now, just a second here. This is the highest frequency so far. And if you take a look at the pattern here, high frequencies have small lengths that we're going to measure. So if this happens, I'm hoping that it's going to happen after this, right? If it happens above this, then we won't notice it right away. And if we certainly go past any of these other ones, then we have too much air in the tube already. Okay. Getting tired of that. Okay.
That was about 18.8.
18.8. Okay. So we did 320, we did 384, we did 288, we just did 426.7, and you'll have to remind me what you just said, Alex? 18.8. Those are pretty high frequencies. Let's try an even higher one of 512. So again, higher frequency is inversely proportional to the wavelength, which means that a quarter of the wavelength here is going to be very small because the frequency is very high. In other words, if we're going to be lucky enough to hear it, it will happen fairly quickly. 15.7. And that's the highest frequency that I think we can handle here. You said 15.7? I do want to add one more. That was 512, I said? I do have that one. I think I have one that's a 4,096 hertz, and it's that really high pitch. But it would happen within a centimeter or two, probably. Let's try 256. I want to try two more. Now, 256 is the smallest frequency we've got so far, which means it can be more than 29 centimeters. So, Alex, you have a lot of time here. That means you also have a lot of time to maybe get distracted. So you need to be patient. And I hope everybody doesn't mind. Alex is just doing this because it's easier rather than moving this around.
Pay attention. Oh, what?
It's not going?
Oh,
Oh, okay, just a second here. I know why it didn't. I got to start that again. The hose is kinked on the bottom.
don't want to do your light again? That happened at about 32.8.
Did it happen there?
It did get louder.
Whereabouts?
32.8.
Would that be consistent with what we've got here? Yeah, I guess it would be, wouldn't it? Let's go with it. It wasn't a very prominent one because I didn't use my knee to bang that tuning fork. The sound itself wasn't that loud. But you said 32.8? And we will do one more. We are going to do 188 hertz. Is that what that says?
128.
128 hertz. I don't know that we can see this one. I don't, or hear this one. I don't think we're going to hear it.
I mean, it's pretty far.
But I don't. Let's try it. Okay. We could certainly do a calculation and find out where it should happen. But I want to just do this and see what would happen.
No harm in trying.
No harm in trying. It's going to be quite a big distance, so I'll just start by doing that.